I hope, could we get started, please? Yesterday we had the French horn, Carolyn van Rennen, and today we are extremely fortunate. We have a violinist with us. We have Ms. Anian Shaw, and I'm very grateful that she is in fact here. Now, yesterday with a horn player here, there was one thing I didn't dare to do, but there are a few people here perhaps who can remember way back to the 60s as I can. Not many of you perhaps, but some. And in the 60s, one of the great comic duos was Michael Flanders and Donald Swann. And they did a horn concerto based on Mozart's horn concerto, and I'm just going to do the first verse. And those of you who know Mozart's horn concerto will recognize it because Swann played the piano and Flanders did the words. And it went, I once had a whim I had to obey it to buy a French horn in a second-hand shop. I polished it up and I started to play it, but despite all the neighbors who begged me to stop. And on they go through the entire movement. It's absolutely brilliant. And those of you who can't remember the 60s or want to hear that can just YouTube Flanders and Swann Mozart, and you'll find it. It's really very good. Okay, but today we're doing strings and violins. And so again, I would like to start historically because archery bowstrings and strings for musical instruments were originally made from from thin strips of the intestines of slaughtered animals, which is why the name gut strings has been assigned to them. With the growth of metal strings, though, we could get greater tension because they could be stretched tighter and could be made more reliable. Many Baroque orchestras today playing what are called original instruments still use gut strings, as do some string quartets in chamber music, such as the London Haydn Quartet or the Austrian Mosaic Quartet, whose motto is, "In gut we trust." I want to start by yet again talking about Monsieur Mersenne, who in 1637 promulgated this law that tells us that the frequency of a string depends inversely on the length. The longer the string, the lower the frequency, the shorter the string, the higher the frequency, and we can demonstrate that, of course. But in teaching difficult concepts in physics, it pays to go over and over them a few times because they are generally not simple. When I did the demonstration with this thing and I waved it and I moved the string up and down, I made one frequency. I got first this frequency, and then by going, or this wavelength, and then by going twice as fast, I got shaking my hand twice as fast, I got this one. I couldn't shake 3 times as fast, I'm not that quick, or 4 times, etc. Now, these, again, this is called a fundamental frequency because it is the simplest thing I can get where both ends of the string are tied down. And then these are harmonics or overtones, whatever you want to call them. And the distance between 1, 2, 3 rest points or nodes, node displacement points, is called the wavelength. So 1, 2, 3 is a wavelength and a half, 1, 2, 3, a wavelength, and another wavelength, 2, etc. So when I did this shaking at the end, I got one frequency. But had I plucked it in the middle somewhere or anywhere along the end and set it vibrating, what you would have seen would not be so simple as this. And what you would have seen is a complicated thing, which is, and we'll talk about this later on, is a combination of these different vibrating frequencies in the string. So we would have heard this one if it were a violin string, for instance, but we'd also hear this one and this one. We'd hear these higher harmonics as well, and this gives a richness to the tone. And the same thing, since a tube, as we saw yesterday, open at both ends, is just like a string fixed at both ends, then in an instrument which is not a perfect tube, but like a French horn, which varies in size as you go down, you also get a rich mixture of various extra vibrational frequencies in there. I think virtually nothing but the violin gives as many and as rich a beautiful sound. Okay, so I wanted to emphasize that once again because it is a difficult concept. Modern violins, the violin family, are based on basically developments that were mastered in the 18th century in northern Italy, mostly in the town of Cremona. And it is interesting, and I will repeat this a number of times, that there's a long history of the development of string instruments, but it reached its peak at that time, and I think not many very significant improvements have been made since. There aren't many technologies which stopped 300 years ago. The earliest instruments we have were so-called open string instruments. They were just plain, simple strings. And the first one, there's a model of a lyre, which was used way back in ancient Egypt and in Mesopotamia. In these, the strings vibrate, but a string is a little teeny tiny thing, and it doesn't get much air into vibration, and so the sound is quiet, is really quite soft. And there are only a few strings, 4 to 6 strings in general in these things, so you couldn't make a lot of music, and that led eventually to the harp. And there's an ancient harp, such as would have been used presumably in the Bible stories by King David. In a modern harp is much more sophisticated. First, it has pedals so that you can change the key or modulate, to use the right word, and there is this big hollow space in here called the sounding board, which increases the volume of the sound considerably. Now, well before Monsieur Marin, musicians learned that by putting a finger on the string somewhere, they could change the frequency. And could I ask our violinist maybe to play an open string and then stop it? It's called stopping, to put your finger on at different places to change the frequency. Look. Thank you. Oh, God. I am in awe of musicians. I just am. They are wonderful. So many more notes were available, and this business of stopping led to instruments with frets on them, such as the guitarra or the vihuela. And you can see, I think, these metal pieces across that allowed the string to be easily stopped in ways. And these instruments were particularly popular in Spain, and leading, not surprisingly, to the modern guitar. In Renaissance Italy, we had the chitarra, or citern, I guess in English, and the zither. The zither is played with hammers, and that may well be what led to the use of hammers in the modern piano. I'm not quite sure about that. And finally, from the Arab world, we had the lute and its older cousin, or its bass cousin, the theorbo. And these instruments have gained some popularity in recent times. All of these instruments were plucked, as you see him doing here, either by the finger or by a plectrum, or sometimes called a pick, if you're doing a lot of it and it makes your thumb sore. And they're made of plastic, of course, today. Now, it seems to have taken a fairly long time before the use of a bow was introduced into stringed instruments. And we had, first in Arab culture, we had this rabab, which is still popular apparently in Pakistan and in some Arab countries. And it can be either plucked or played with a bow. Notice again this thing which in a modern violin is called the middle bout, which allows greater access to the strings. And this was one of the earliest of instruments, although it is still in use. And then eventually we have the rebec and the lira de braccio, or the lyre of the arm. And this now begins to look like a modern string instrument. I don't know if you can see, it's got 1, 2, 3, 4, 5, 6, I think 7 strings. Notice also the bow looks rather like a hunting bow, quite an unusual thing, very different from what we've got. There were several centuries of experimentation with creation. What I do want you to notice is that all of these instruments have the strings attached to a box, a wooden box, and the box has holes in it. And that, as we shall see, is extremely important. But we have first the introduction of the viola da gamba, of the leg sitting down, and here's the braccio, the arm. And I'd like you to notice that there is no chin rest on this instrument, and so the cheek is holding it down, but so is the forearm of the player. This is probably quite realistic because this is supporting a lot of the weight. I would think that that would limit the ability to move up and down the fingerboard here. In more modern violins, as I'll point out later, of course, there's a chin rest, and it always frightens me when I see before a concert a violinist with sort of there with the violin sticking out, and I'm sure somebody's Strat is about to fall on the ground, but I've never seen that happen, so I guess it's okay. Now, these instruments generally had a lot of strings, and they were tuned usually a fourth apart. But again, with the introduction of more metal strings, shorter strings were used at higher tension, and it was reduced to only 4 strings at higher tension, and they were tuned a fifth apart rather than a fourth. And the braccio led, of course, to the wonderful instrument we have today as the violin. So I have here a picture of a violin with the names of the parts of it, and you can see there's the chin rest that I was talking about. This is one of the very few things that is later than the era of Cremona. This was invented or first used by Ludwig Spohr. He put this on, I think, in 1820. Here is the tailpiece, there's the scroll, the neck, the fingerboard, the belly, the middle bout, the lower bout, the upper bout, etc. And the very important fholes. This violin has, I think, 4 fine tuners on it. I think most violins only have a fine tuner on the E string. Now, I have another picture, which I rather like because it has numerous misspellings on it. First, it's a tunning peg here, which is wrong. And secondly, they've put violin here when they meant to put viola. But again, we can see all the different parts. And in particular, it shows where the sound post comes, which is under this part of the bridge, this being the bridge. And it is a crucial thing. And here we have, of course, the belly. And here we have a modern bow. and the modern bow has horsehair on it. Notice that the stick moves toward the hair, not away, as in the old bows. So, as I mentioned, strings only cause a very small amount of air to vibrate, but and they make a weak sound. The sound of the violin comes from this marvelously shaped wooden box. But first I want to talk about bows a little. Oh, no, sorry, let me show you the internal structure first. There is the sound post, which is rigidly fixed underneath this piece of the bridge, and it means that this piece cannot move because it's attached between the belly and the back plate. And then underneath this piece of the bridge is this bar called a bass bar, and we'll talk more and more about that. This is, these two things are what help the violin to make sound. But first I want to talk a little bit about bows. Here we see some of the early bows, again with the stick away, pretty much away from the hair. And there's a more modern bow in the opposite direction, the frog, the tip, and the hair. Okay? And a screw for tightening, of course. The hair used is horsehair. Okay? And the reason for horsehair can be seen in this slide, which is a magnified view of horsehair. And you can see it's got little scales in one direction. And if you put rosin on the bow, it only enlarges these things. And it is these that catch the string that actually make the string vibrate, as we shall see. Because the use of a bow is what is called a stick-slip phenomenon. I don't know why that's backwards. Anyway, so that it catches the string and it pulls it and then it lets it go and its string snaps back, and then it catches farther down and it pulls it and it snaps back, etc., over and over and over again. And that's what makes the string vibrate. But as we shall see, it's a very complicated vibration. So friction is what makes things move. First of all, since violinists bow in both directions, up bow and down bow, could I have you just do that for a second? Yeah, now, I don't hear a difference, but I've talked to conductors and they claim they absolutely hear the difference, and down bow is much better, and it's, but you know, I'm not that sophisticated. Because of both up bow and down bow, hairs are put on the bow in opposite directions so that these little scales catch. So the construction of a good bow is a serious and expensive matter. They're not, they don't cost as much as a Strad, but they're not cheap. But it's friction between the bow, between the hair and the string that causes the sound. And so I want to mention a few things about friction, because friction is important. Friction comes in two kinds. There's static friction, getting something moving, and there's moving friction, or to use the proper Greek word that scientists use, kinetic friction, which is the friction involved when something is already moving. And I think anybody who's ever pushed a heavy object over a floor knows that it's harder to get it started moving than it is to keep it moving once it's going. It's not hard to understand why friction works, because if I look at a surface on a microscopic basis, that is atom by atom, there's nothing smooth. Okay? Atoms are incredibly small. There's no such thing as a smooth surface. So this would be what a surface looks like on an atomic scale. And each of these little bumps would be, say, a single atom or a couple of atoms. This atom and this atom are repelling one another or attracting one another by electrical forces. And so there is a repulsion here, meaning that it is hard to get the thing moving. I've got to overcome that electrical repulsion. The electrons in this atom are pushing away the electrons in that atom. And as most people know, like charges repel. And so, however, when the thing is in motion and this is already snapping away, it may be already way over here when this thing comes by, or this one may be over here when this comes by. And so it's easier to keep it moving. Also, I think it might be fairly obvious that if you put oil on the surface, it floats, and that would reduce the friction. But that's, of course, exactly the opposite of what one wants to do in a violin, which is put rosin on to increase the friction. Okay. Now, the bow grabs hold of the string, and it pulls it. And it pulls the string. But as you pull a taut string, you increase the tension, and it pulls and pulls, and there's what's called a restoring force, a force pulling back against something that I think you can realize is true. And there's a restoring force pulling it back, and eventually, as the restoring force gets bigger and bigger, the string is released, bunk, and off it goes, and then it catches again, and it's released again, and so forth, over and over and over. And so what you really see for the oscillation is pull, 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 snap, pull, 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 snap, and you get not a smooth repetitive curve, but a sawtooth kind of curve like this. Now, this kind of curve is what we saw yesterday, in where I take this object and I just let it go. Now, if I put a pen on the bottom of that, and I had a piece of paper underneath, and I pulled the paper across at a uniform speed, the pattern that would be made would look like that. It's me somehow, I don't know what that is. The pattern I would get on the paper would look just like this. This thing is feeding back somehow. Maybe it's too close. I'll move it a little farther away. So I would get this kind of a pattern if I just drew the motion and had time going this direction. And this kind of pattern is both harmonic, which means it repeats, and it's simple harmonic because it repeats in the simplest possible way. This motion is also harmonic, but it's far from that, and it's not simple. And analyzing the motion of a violin string is not a trivial thing, but we know how to do it. Because back in the 19th century, early part of the 19th century, a very clever French mathematician named Joseph Fourier showed us that any repetitive function, no matter what its shape, whether it's a triangular sawtooth, whether it's a bunch of triangles, whether it's something that goes straight up and across and then down and up, like so what's called a square wave, no matter what it is, can be constructed, reproduced by adding up an infinite number of ordinary waves like this of different frequency. That's a complicated thing. Let me show you how that works. If I take the sawtooth wave, such as we saw, okay, and I take just 6 different sine waves, the red one and there's a blue one, which is twice. You see, this is one bump, there's two bumps, okay, and then I've got 3, 4, 5, and 6 bumps, I think. If I add these all up, I get this kind of a shape, which is almost a sawtooth. And as I keep adding more and more and more frequencies, I get closer and closer to that shape. And these corners require very high frequencies, but what I'm really doing is adding all of these up to infinity. Okay? And so there we see the same, this diagram. But what Fourier, this is called Fourier analysis, and is something that's used in your mobile phones. But it allows me to say that what happens in a violin string, which is oscillating like this, is a combination of a large number of harmonics. And that's adding up a lot of these different frequencies, a lot of these harmonics, is what makes the violin have such a rich and wonderful tone. Okay. Now, bowing is, of course, crucial to the sound. So what I'd like to do is, again, ask Anian if she would bow first a string, but then to put the mute on and change the vibrations of the bridge so that you can hear the difference. Great. And that's because it is the motion of the bridge that is causing the violin to make its sound, as we will hear or see. Now, let me go back to this picture. Okay, one end of the bridge, this end of the bridge, sits right over the sound post, and therefore it cannot move. But the other side of the bridge can move, and it is over this piece, which is not fixed to the bottom plate. The top plate of a violin is generally made from a fairly soft wood. It can be spruce or pine or something. The ribs and the back plate are made from a much harder wood, often maple, I think, and the fingerboard is usually ebony. And it's curved these days to give greater ease of reaching the strings. Now, so what happens when the string is pulled sideways? Here is a picture of the bridge sitting over the sound post, and here's the other end over the bass bar. So when the string is pulled sideways, let's take the A string here, the bridge will rock. And that rocking will then move the belly up and down. And the bass bar will move, and that means not only the belly right here moves, but the whole belly moves. And so this thing is vibrating, and that vibration of the belly also is transferred to the air inside the violin and causes the air in there to vibrate also. There's another tiny effect, because the string is fastened at both ends. And so when it is moved, it not only moves like this, but it also pulls the bridge slightly in that direction, a teeny amount. And that motion of the bridge in this direction is actually at twice the frequency of this motion, and it introduces a harmonic, which can be a distortion problem, although it's quite small, but it is real nonetheless. In any case, what's vibrating is the air inside the box. Now, what I think we can do is, and this is tricky, but the reason for the F holes here is to allow the sound to come out. And so what Onion has agreed to do is cover the F holes with a cloth, and so you can hear the difference when the sound can get out and when the sound can't get out. Yeah. Oh, that's tricky, yeah. Softer. Softer. And one is still open, right? One is still open. Good, thank you very much. Now, there's a phenomenon in science that is, I think, fairly easy to understand. Oh, here is the bass bar on the belly. There you can see what the original Baroque one was, and this is what the more modern one does, and then you can see it, how it reaches across the entire belly. But there's a phenomenon which I want to talk about called resonance. And resonance is easy to understand because any of us who have ever pushed a kid on a swing know what resonance is. You start the swing moving, and it has a natural frequency. And so the child, of course, wants lots of amplitude, and so you push. And how do you push? When the swing comes up, you push the swing when it's here. So you are pushing every time it comes back up. And therefore, you are pushing with a frequency which is equal to the natural frequency of the swing. That's called a resonant frequency, and it increases the amplitude of the swing, how far it goes. Now, if you are a dad like me and you're talking to a cute mom at the next swing and you're not paying attention and you just push on occasion, the kid will complain because you're not pushing at the resonant frequency. So resonance is an important problem. It's when the external push is equal to the natural frequency of vibration. Strings have fairly straightforward natural frequencies, but air and wood do not have simple natural frequencies. And so resonance in those systems is much more complicated. So the wooden surface and the air within the violin body have their own frequencies, but they are they're complicated frequencies, and they're not well defined. And there's a band of frequencies around some central value. So I found on the web this following frequency response for 4 different violins. There's a green curve, which is the frequency response for a Stradivarius, okay? And these are resonant frequencies. Here is the frequency. This is 500 hertz, which is slightly above concert A is about here, 440. So this is roughly a C. And here's 1,000, 1,500, 2,000, etc. And so the Strad has a strong resonance at about 750 vibrations per second, or hertz. The blue is a Del Gesù violin, which notice has a similar wood and air frequency. The yellow is Bergonzi, and the red is a cheapy violin. And notice that this has really strong resonances, well above what the normal vibrational frequencies, but right in the harmonic range. And this is a problem. So An air resonance, the resonance of air is about here, about 200 and this is 500. It's about 280 hertz, and the resonance of wood is generally around 420 hertz, which is just below concert A, and it's probably this thing here, and you can't really get away from that. So what the great masters have done is they have concentrated on the place where the harmonics are, and then they try to make a good frequency response where the natural resonant frequency of the fundamental of a string would be. Okay, and that's what constitutes, in a technical sense, a really good violin. They must have experimented like crazy to get this to do, because making a violin is an extraordinarily complex business. And what really matters is the wood, and the thickness of the wood, and the grain of the wood, and how you shave it, and so forth. And so this was all done, of course, by trial and error. And the great Cremona, the Amati and Stradivari and Guarneri and Bergonzi and Ruggeri, these great people who made these masterpiece instruments, had generally were usually very guarded because they had trade secrets that they had discovered, and they didn't pass them on very well, with the exception of Amati, who had a student named Antonio Stradivari, and he taught Stradivari how to make violins. Stradivari lived to be 93 years old, so he had a long career, and he seems to have made about 1,200 violins, and we have today 550 roughly that are playable. He also sold them for relatively low prices, so they were quite popular. Now, of course, they go for prices that are beyond the lifetime income of most human beings. There has been a lot of folklore, at least I heard years ago when I was paid more attention to music, about the varnish used on Cremona violins, as if that somehow made a difference. And the formula for the varnish has vanished. Nobody knows what it is. Nonetheless, any kind of scientific test ever done of that has shown that there is basically no effect. People have done careful X-ray analysis of the wood and looked at the grain of the wood, and what they find is it's very fine, long grain, and the vibrations of the wood are along the body of the violin and not perpendicular to it, and that seems to make a significant difference. But wood is a very complex structure, and as I've said, and there are a number of resonant frequencies which depend on the grain structure. These resonant frequencies are generally between 3 and 6,000 up here. And they are a range of frequencies, and a range of resonant frequencies is called a formant, F-O-R-M-A-N-T, formant. And this is an important word which matters a lot to string instruments, and as we shall see on Friday, matters a great deal to the human voice and singers. The formant is, of course, again, relatively good in these old Cremona instruments and not so good in poorer instruments where the resonances tend to be sharp. There's an unfortunate thing about wood resonances that violinists have to take into account, and that is if you have a string which is resonating very close to a wood resonance, then you get a sympathetic vibration where the string tries to